Okay, so the last thing we're going to look at in 5.1 is two types of formulas, one for exponential growth and one for exponential decay. So what you're going to be given in this problem is some information, and you're going to plug it into a formula and then simplify it. So the first formula we're going to look at is the one for exponential growth. The formula has three variables in it. So a kind of problem you might see is, let's say you had a population of a town with 20,000 people, and it's growing at 2% every year. One thing that you need to know when you're doing exponential growth is how many things you started with, whether it's an amount of people, an amount of money, amount of bacteria, whatever's growing, you need to know what you started with. That's your initial amount. Okay, next thing you need to know is your rate of increase. So what is it growing by? Is it 2%, 3%?
Is that 1 plus r? Or
1 plus r, yeah. Right? It's going to be some kind of percentage. That's your growth rate. When they give you the problem as a percent, you need to change it to a decimal. So if you had a growth rate of 5%, what is that as a decimal? 0.05. Okay. If you had a growth rate of 13%, what is that as a decimal?
0.13.
Yes. Yep.
So pretty much any number up to 10 is of that number, and then anything after that is just point that number?
Yeah.
Unless it's over.
Yeah, it won't. We probably won't be doing over 100.
Okay. What's
like,
the T?
And T, that's the amount of time. So for example, if I said the population of the town is 20,000 people, it's growing at 2%, tell me what the population is in 15 years. T would be 15 years. Okay, so that's the formula for exponential growth. There's only one thing that changes when it's exponential decay.
Is it -1 minus r?
Becomes 1 minus r. Yep. So everything else is the same. Okay? So you have to be able to read the problem and figure out if it's growth or decay. The way you would know it's growth is you'd see a word that indicates something is increasing. The population is increasing, it's going up. Decay would be something about decreasing. The population is going down, it would indicate dropping. Okay, so that's the exponential decay formula. That's exponential growth. Okay, everybody have those two formulas.
Why do we need the 1 in there? Can't we just do like p plus r, p minus r in parentheses with the t on top?
Because when if you don't put the 1 in, it's not going to calculate the growth or decay correctly. Because let's say something was decaying at 10%. You wouldn't want to put 0.1 in here. You'd want 0.9, okay? Because that represents you only have 90% of what you started with if it's going down by 10%. That's why we have to subtract it from 1. Yeah. And same thing here. If it's increasing by 10%, then you would want this number to be 1.1, because that represents 1 is like what you had before, and 0.1 is what you're adding to it. So it's 1.1. All right, so let's look at this one. And first, when we read it, is it about exponential growth or exponential decay?
Growth.
Yeah, this is about exponential growth. And the key word that tells you that is it's increasing. And it's increasing at a percentage. If the population of a town was increasing and it said something like the town gets 500 new people every year, that's not exponential. That's just adding 500. In order for something to be exponential, the rate has to be a percentage. It can't just be a fixed amount that you add every year.
How do you change 2.5 to a decimal? Oh wait, 2.5. Wait, why? Do we just keep it as 2.5 and get rid of the percent sign?
No, we still have to change that to a decimal.
How do you do that if it's not a whole number?
Well, what if you had 2%? What would that be as a decimal?
0.02. Would it be to 0.025?
0.025.
Oh, okay, I get it.
So when you get to that, we're gonna have to do that. So two things they want us to do. First, basically write a formula. That's what they mean by model with a function. And then once we have that, we're gonna graph it, and we're gonna figure out when the population hits 100,000 people.
For the time, do we write 1 because it's 1 year?
They don't give us a time. They don't give us
This
any.
says per year. So could you do it for 1 year and then multiply it to find the?
Well, if they said find the population after 1 year,
So we would just add a 1 if it said that?
if it said that, yeah, you could put a 1 in for t.
So you don't necessarily need to have a time?
No.
Okay,
Nope. That could be something you have to solve for.
okay.
Okay, so this question does not say find the population after 1 year. It's kind of the reverse of that. It says find when the population is going to hit 100,000. So you're solving for time when we get there. All right, so let's start with our formula. Let's call it the population of the town as a function of time. So I'm calling my formula P for population. And T means that's the variable that I'm going to be using on the right side. Okay. Since it's exponential growth, what's the first thing that comes after the equal sign?
The initial amount,
Initial amount.
which is the 50,000.
So that's, yeah, initial amount, it means the same as like the starting amount. 50,000. And then what do you put in parentheses after the initial amount?
1
plus 0, or 0.05.
Right, it's 1 plus r. And in this case, we just talked about r, 0.025. Alright, and there's still one more thing I need there to make this an exponential equation. Time. And where is the time going to go?
The exponent.
The exponent.
But since there's no time, what do you do?
We just leave it.
So we just don't do it anymore.
Yeah, we leave it as t.
So why do we add it?
Because it needs to be in.
Well, without a variable exponent, then you don't have an exponential equation. Yeah. Okay, so our final formula for the population of the town, based on the number of years that have gone by, is 50,000 times, what's 1 plus 0.025?
1.02.
1.025. Okay, so that is the model that represents this problem. Okay.
Why didn't you distribute? Couldn't you have done either? You could have done.
Well, when you have something raised to an exponent, PEMDAS, exponents always come before multiplication. So you can't do a distributive there because you have an exponent.
In this instance, I don't think it would change your answer though, would it?
Yes. Yeah. So when you really want to just follow PEMDAS, so do your parentheses first, and then you can't multiply 50,000 times 1.025 because that has an exponent. It's kind of like if you had 8 times 3 squared. You can't say 8 times 3 is 24 squared. Even though 8 times 3 is 24, you can't do that. You've got to do 3 squared is 9, and then 9 times 8 is 72. Okay. You gotta follow order of operations. All right. Now the second thing is find when the population hits 100,000. There's 2 places we can plug in 100,000. Is 100,000 a time, or is 100,000 an amount of people?
An amount.
It's an amount of people. So that means it's going to get plugged in on the left side. If the question said find the population after 10 years, that would be different. Then you would fill in 10 for t, because that would be time. But that's not a time. It's an amount of people. Okay, so put that in.
100,000 equals 50,000 times.
Yep, 50,000. And now we're going to solve that on the calculator. What do you think I'm going to put in y1? 100,000. Okay, so let's type in 100,000. And what about in Y2?
What do you do the 50,000 times whatever to the?
Why are we graphing this?
Because it has a variable in the exponent. So we're answering the second part of the question. When is the population 100,000 people? Unless we know logarithms, we're not going to be able to get that variable by itself. And we eventually do logarithms, but we haven't learned them yet.
Does the year come out to like an even number or something?
No. No. It's not a very not nice number. So the only way we know how to solve it right now is the same approach we use when we don't know how to do algebra on any equation. We graph it and take that approach. So we got 100,000 in Y1. We got 50,000 times 1.025 to the x. So I'm going to graph each of those. And what am I going to look for?
When they intersect.
When they intersect. Now Y1 is at 100,000. So is the standard window going to be okay?
No.
No. I would probably go up to like 110,000. So that gives me a little bit more on my Y max. So we're definitely going to see the line, but the question is, can we see where the curve hits it? No. We didn't go far enough out. What do I need to set higher to see where they cross?
Your
Yep. So let's set the x max. Let's set it up to 30. And that should do it. Guaranteed. Yep. So now we just have to see where they cross, and that's how many years it's going to take for this population to hit
What did you
100,000 people.
Set your x min to.
it's going to be 2.
My x min, I think I did 0.
All right.
Because it doesn't make sense to look at negative time. Negative time or negative people. Well, there are negative people, but there aren't.
Mine keeps giving me an error. What did you set your y min to?
My y min, 0.
What do you set your y?
Y max is 10.
What's the y max of what?
110,000.
And now when we graph it, we just barely we can see where they cross. What do I press to see where they exactly where they cross? Second calc.
Intersect.
Intersect. Because they only cross one time, it doesn't really matter where we put the cursor. Just hit enter.
I still can't see it. What is your sense? What is
can't.
the window set for again?
The window, right there.
I when I see it.
So it's 28.077 years.
Yeah, it's going to take about 28.07 years for this population to grow to 100,000 people.
And then you go to. Sorry, I just got it so I can see it. Then you go to intersect and.
Yep.
I got 40 years because I don't know. I just like because I did like the 50,000 people and I did inside the parentheses 1 plus.
You just said you can't do that. Because
What?
there's an exponent that has a letter. You have to do the exponent first because of pen does.
I mean, if you start with 50,000 people, I mean, you can go like this. This isn't a great way to do it, but that's how your population after 1 year.
Yeah. So
And then if you do it again, that's 2 years, 3 years, 4, 5, 6, 7. I mean, you can keep going. Now that's after 10 years, right? It's not going to give me an exact answer. That's 13 years, 14, 15. Eventually, I'm going to get 17, 18, 19. That's 20 years. So I'm going to get close, but I'm not going to be able to get 28.07.
Well, if you go back to the beginning, it said like 1,025. So that's like per year, right?
No, the growth rate isn't linear. It doesn't add the same amount of people each year. Because it's going up by a percentage, 1 year it may add 1,100 people, the next year it might be 1,300, and then the next year it's 1,500. So the number of people being added each year is increasing. Yeah. Yeah, that's what makes it exponential. If it just said add 1,000 people every year, then the growth rate would look like that. It would just be a straight line. But this is more of a curve. Okay. So any question on how we got 28.07 years?
No, I just want to do this like 5 more minutes.
Yeah, we got a couple more.
Couple more.
Let's try this one.
It's difficult.
So, as I just mentioned before, be careful about including negatives. A lot of times negatives don't make sense in a word problem because you can't have negative amount of years, and you also can't have negative people.
So you just
Well,
take
again, you can
absolute-
have negative, there are negative people, but you can't have negative amounts of people.
So you just take like the absolute value.
That was a joke.
I just,
No, you just set your y min and max at 0.
Oh,
Yeah. So a lot of times looking at negatives, it just doesn't make sense in a real world problem because there's no such thing as a negative for that quantity. So now we're going to look specifically at growth, but this is going to be something doubling. Okay, so this is a lot faster growth than the last problem. Okay, the population in the last problem was only growing at like, I forget what it was, 2% or 2.5%. Doubling is much faster. So we're going to start with 100 bacteria, and it's going to double every hour. So what I want to do is look at the pattern and then see if we can figure out a formula for something doubling.
couldn't you just do this the long ways too and do 1,000 or 100 times 100 and then do that
Yeah,
times
100
itself and then do that times itself?
So you can kind of estimate it, but it's not going to give you an exact answer.
No?
No, because if I said when does the bacteria reach 500, it's going to be in between numbers. Because like it's going to be 100, then it's 200, then it's 400, then it's 800. It's like you skip over 500. So it happens in the middle. So to figure out, especially something that happens in the middle, we're going to need a formula. So it's going to be very similar to this formula because it's still exponential growth. It's just, it's a very specific number for R.
So
We got to figure out what R is when
R
something is doubling.
1.5.
Well, you'll see what it is. So when this experiment is starting, that's time 0. Time 0 means the beginning. How many bacteria do we have at the beginning? We have 100, yeah. After 1 hour, how many bacteria will we have?
200.
200.
Doubling.
Oh, doubling, sorry. I thought it
Yeah.
was 50%.
Nope, if it was increasing by 50%, then yes, it would be 150. But this is doubling. So we have 200. But I don't want you to think of it as 200. Okay? I want you to think of it as in a way you can figure out the pattern. It's the initial amount times 2. Let's look at the next one. How many bacteria would you have after 2 hours? 400. And again, think of it as the initial amount times 2 to the second. How many bacteria would you have after 3 hours?
800.
800. And what do you think the formula would be for it? 100 times 2 to the third. Initial amount times 2 to the number of hours that have
So the
gone by.
exponent matches the time.
Yes, in this one it matches the time. So how about this?
2 to
T
the
hours.
t.
100 times 2 to the t. Yep. So in general, the formula for something doubling is the initial amount times a 2. It's always a 2. It's not a 1 plus r when it's doubling. 1 plus r is kind of general, but this is specifically doubling.
So that's the formula, 100 to the t.
Well, if you started with 100 bacteria,
okay.
but it might not always be 100. You might start with
But if it's doubling, it's number times 2 to the t.
times 2 to the, this is what we always need to put.
Yep.
Now, in our problem, the bacteria was doubling how often?
Every hour.
every 1 hour. So really, it was t divided by 1. When you divide by 1, does that do anything to it? No, that's why I didn't bother with that. But if the bacteria was doubling every 3 hours, you have to put a 3 in the bottom if it was doubling every 3 hours. Because this represents the number of times it has doubled. Not necessarily the number of hours that have gone by, but it represents the number of times it has doubled. Now, if it doubles every single hour, then yes, they're the same. 5 hours, it will have doubled 5 times. But let's say something doubled every 3 hours. If something doubles every 3 hours, and 3 hours have gone by, has it doubled 3 times? No. How many times would it have doubled?
Once.
Just once.
Okay.
How about in 6 hours? How many times would it have
Twice.
doubled? It would have only doubled twice. And that's what this exponent has to be. Okay, the number of times it is doubled. And that's how you figure it out. Take how much time has gone by and divide it by the length of the time to double. All right, so let's try this one. So we are going to do an example with 100 bacteria. And it's doubling every, let's just change that. Let's say it doubles every 2 hours. So if it doubles every 2 hours, after 2 hours, it hasn't doubled twice.
Once.
It's only doubled once. Okay. So when we write our exponent, we're going to have t divided by 2. So first of all, is this growth or decay?
Growth.
It's definitely growth. If something's doubling, it's getting bigger. Okay. The last one we're going to do is a decay. Okay, so 100 bacteria doubling every hour. We want to know how long, every 2 hours. Sorry. How long before we hit 350,000? Now, you might think it's going to take a long time, right? Because you only had 100 and you're trying to get up to 350,000. But really, it doesn't take that long. Because doubling, things increase very quick. Okay, so let's do our formula.
It would be 100 and then in parentheses 2 to the t over 2.
So, yep, so I'm going to use A to stand for the amount. So A stands for an amount of bacteria as a function of how much time has gone by. So, yep, it's 100 times what?
2 to the t over 2.
Yes. Just a coincidence, they're both 2's.
Yep.
This is always a 2 when something doubles.
Alright.
That's a 2 because that was a 2. All right. So there's our formula. And now they want to know when we're going to get 350,000. Is 350,000 a time or an amount of bacteria?
No,
It's an amount. Where does that 350,000 go then?
not the beginning.
On the left side.
Yeah, on the left side, yep. If I said to you, how much bacteria will there be in 10 hours?
You would put 10 for t.
Then you would plug the 10 in for t on the right side.
Are we ever going to do one of those?
Yes.
They seem a lot easier.
Yeah, they're a little bit easier. You don't have to graph them.
Yeah.
Yeah.
I don't like graphing.
Okay, so we're going to figure out when we hit 350,000. Okay, so what would I put in Y1?
The 350,000.
350,000, got it? What would I put in Y2?
100 parentheses 2 to the
X divided by 2.
X divided by 2. Now, the window I had last time is not going to work. What should I set my Y max to?
360,000.
Yeah, we could do 360. You could even probably just do 400,000, just as long as it's higher than 350. All right, we can leave it at 30 and see if that's enough hours. Let's think about it for a second. This doubles every 2 hours. After 30 hours, how many times will it have doubled?
15.
It will have doubled 15 times. So we're going to see if you double 115 times, does that get you to 350,000? I think the answer is going to be no. Nope, I was wrong. So it does hit it. It doesn't look like it's going to go up fast, but then all of a sudden it just takes off. So let's figure out exactly how many hours it takes. How do we do that?
Second count.
Intercept.
Intersect. So if you have 100 bacteria doubling every 2 hours, it's going to take just under 1 day,
23.5.
23.5 hours. Yeah.
Would you not do roundup for the second one?
So if you're going to round to 1 decimal, it's 23.5,
Yeah.
or 2 would be 23.55. Yeah. Okay, so just under 1 day to go from 100,000 bacteria to 350,000. All right, any question on that one? Okay, so that's doubling. What do you think the opposite of doubling is?
Depleting itself?
Dividing.
Well, it's, yeah, what would you be dividing by?
Itself?
2. Yeah, and that would be halving. Yep. So the last one we're going to look at is what's called half-life.
What's it called?
Half-life. So half-life is the amount of time it takes for half of a substance to disappear. Okay, a lot of times you see that with like nuclear radioactive stuff. So when you have a nuclear power plant, there's waste that's made, and some of that waste may have a half-life of, say, like 1,000 years. That means if you have 10 pounds of nuclear waste today, in 1,000 years,
It'll be half.
it'll be half that. You'll only have 5 pounds. And then after another 1,000 years,
You'll have 0.
you'll have 2.5 pounds,
Oh.
because it keeps getting cut in half.
Oh, I thought like half of it would be like half of its life and then the other half is like.
Yeah, no, so half-life means it basically divides by 2 every 1,000 years.
Okay.
So let's say if you had 10 pounds today and it's not safe until it's under 1 pound, well, half of 10 would be 5, and then half of 5 would be 2.5, and then half of that, and then you'd probably have to go half again. So we have to go through 4 half-life cycles. And if a half-life cycle is thousands of years, basically it takes a very long time for nuclear material to be
So
safe.
it's just doubling but dividing instead of multiplying.
Yeah, it's the opposite of doubling. It's halving. So when we did doubling, what was the number we had in parentheses?
2.
2. What do you think the number will be for halving?
2. 1/2.
1/2. Yep. So it's 2 when it's doubling. It's a half when it's halving. But other than that, the formula is exactly the same. You get the initial amount. 1/2 represents the fact that it's a half-life problem. And then this is the number of half-life cycles that have gone by. If the half-life cycle is 1, then the number of half-life cycles would match the number of hours.
So it's like it's the exact same thing except you're dividing.
Yeah, except it's 1/2 instead of 2.
Yeah.
Okay, so we have a radioactive substance that has a half-life of 20 days. That means every 20 days that goes by, you're going to have half of what you had. And we're starting with 5 grams. We want to figure out, well, we're going to write a formula first, and then we're going to figure something out. So let's do the amount of stuff as a function of time.
So would it be 5 to
So
the
5 is the initial amount.
yeah.
And then what's in parentheses because it's a half-life?
5 times 1/2
Okay, and you know it's a half-life because it's the first word in the problem, half-life.
to the t over 20.
Yes. So if you plug in 20 here, what's 20 divided by 20? 1, because that means after 20 days, 1 half-life has gone by. After 40 days, 2 half-lives. So our question is to figure out how many days will it take to do something. I haven't shown you that yet, because that's the next question. there's your formula. Any question on the formula? Okay, so now the question is, when will we have less than 1 gram? Well, it's definitely more than 20 days, because after 20 days, that's 1 half-life. At 20 days, you're going to have 2.5 left. So we got to go more than 20 days.
It's 30 days. I mean, 60.
So we want to know when there's less than 1 gram. So first thing we want to do is figure out where that 1 gets plugged in. Is 1 time, or is it an amount?
Amount.
It's an amount. So we're going to plug in the 1 on the left-hand side. It's exactly the same as when we did the people, right? Same thing. 1 equals 5 times 1/2 to the t over 20. Okay. Again, the reason we're graphing it is because at this point, we don't know how to solve an equation that has a letter in the exponent. To do that, we need a logarithm. We are going to learn logarithms. It's going to be part of what we do in the trig. And that's not going to be for a while. It's going to be quite a while. So we're going to graph it. Okay. What would I put in y1? 1. And y2? Yeah, you could do 1/2. You could do 0.5. That would be silly. X divided by 20. Now, I only have to look as high as 1. So 400,000 is way too high. So let's set y max at, yeah, like 2 or 3 or 4, somewhere around there. So we got a line at 1, and then you're going to see your substance decaying in red. Okay, so if I let me set the y max higher so you can see what's going on. So remember, we're starting with 5 grams of this, and it's going to decay down. And I want to know when I'm under the blue line. Okay, so when am I under the blue line? Farther out than 30 days. It's going to take longer than that.
50.
So yeah, let's go to 60. Okay, so there's my level at 1 gram. Here's my substance decaying.
And then you just do the intersect thing again?
Yep. Now, I can keep looking further and further to the right, but what is this red line never going to reach?
0.
It's never going to reach 0. So what that basically means is once you create like a nuclear waste, it never goes away. Ever. Even after millions of years, it's still there. It just gets less and less and less and less and less. Okay?
So where does the stuff that went less go?
I think when they talk about half-life, they mean it like breaks down into something that's safe. Maybe, I don't know if it breaks down into like carbon, and I don't know the chemistry part of that. But it breaks down into something that's not radioactive anymore.
Yeah. 46.4 days.
All right, so second calc intersect. So it's going to take 46.4 days. For you to have, well, that's how many days it takes to have exactly 1 gram. Yeah, 46.4 days. The question was, when will you have less than 1 gram?
You just put like parentheses around it.
46.5.
Yeah, anything above 46.4. Because the more days that have gone by, the more it's going to continue to decay. So anything from this point onward. Yes?
So,
Yeah, just sign out for me.
so 46.5 would be the answer?
I would just say anything greater than 46.4. Or if you want to go to 2 decimal places, you just have to be above that number. Okay, if you're equal to that number, you've got exactly 1 gram left. If you go past that number of days, then you're good. So greater. Any questions why it has to be greater and not equal?
If this nuclear substance is always halving itself, what happens, like, can it ever be 0?
No. No. It's the same thing with like medication. when you take a medication, it has a half-life. So once you take that, like let's say you take 1 gram of something, and then it has a half-life of a day. At the end of the day, there's half a gram left in your system. At the end of that day, there's a quarter of a gram. At the end of the next day, there's still an eighth of a gram. Eventually, there's so little left, it doesn't make any difference. Yeah, and it basically turns into nothing.
That's cool. I didn't even do that.
But that's how a lot of medications work too.
Is that why some of them are fast acting and some of them stay in your system for a long time and work for longer periods of time?
Yeah, if the half-life was say like 8 or 9 days, then it takes a very long time for that.
So it works for like a longer period?
Yeah. Yep. And if you take the medication at the same time every single day, then eventually that level of medication starts to stabilize because you have medication in you for weeks and weeks and weeks, and now it stabilizes. But when you start taking it, it's kind of all over the place, and then it stabilizes. Yeah. All right. Any question on that? Okay. So that was the last part of 5.1.
Are we gonna get one of those like packets to review today?
I am going to put a list of topics up, and we've got about 20 minutes, so I could give you some sample questions. But no, I don't think I have like a packet ready.
I would love a packet, so if we could go over
I
example
think
questions
that-
back to maybe my own packet, that's good.
All right, I gotta change that because we did some of that last night.
Yeah. I like the
We did 4
packets.
through 7, so.
Yeah, we did the 4 through 7. Yeah, we're not doing that one.
Somebody-
Okay, so we're gonna do. That's a bacteria problem, 47 to 49.
This is 5.1.
Yeah. That's a half-life problem. And that's another half-life. So there's exponential growth and then a couple exponential decay. Oh,
Don't say that's it.
no, I can come up with another one.
No, I'm all set. No?
Do you
We have
want,
a test tomorrow, we
do you
gotta
want one
study.
about rabbits
No.
multiplying?
We gotta,
No.
there is
I
number
suggest you never
Number
say that
50 is
again.
about rabbits.
we gotta study
Oh,
today.
I like you, but
His first one, I knew it. I said,